acyclic is a matroid. So today we'll be looking at properties of matroid. This is something that we saw towards the end of the lecture, which kind of essentially gives us the greedy structure, okay, or describes the greedy structure. So suppose M is a matroid with E as a ground set and I as a collection of independent sets. Now a basis is a maximal independent set, okay, so that is a set which is independent such that no superset of it is independent, okay. So that is A is a basis if for any B such that A is contained in B, properly contained in B, B is not independent, okay. So yeah, so we use the word basis or basis of a matroid or maximal independent sets of a matroid. As we saw in the last lecture, basis of a graphic matroid, if the graph is connected, is a spanning tree. If it is not connected, it's a spanning forest, that is spanning tree for each of the connected components. Okay, so we look at an important property which we saw towards the end of yesterday's lecture. If you take any two bases, that is maximal independent sets in a matroid, then their cardinality should be the same. Okay. So this is a very simple argument. It just follows from the exchange axiom of matroids, exchange property of matroids, that is I3. Okay. So let's quickly prove it. So suppose B1 is smaller than B2. Okay. So then by I3, so remember that B1 and B2 are both independent. So the independence axiom 3, that is exchange axiom. So there is an E in B2 minus B1 such that B1 union E is in I. So this is a contradiction to the maximality of B1. So therefore, cardinality of B1 cannot be less than cardinality of B2. Similarly, cardinality of B2 cannot be less than cardinality of B1. So therefore, cardinality of B1 must be equal to cardinality of B2. That's the only possibility because these are natural numbers. So this is the only possibility. Either one is strictly less than the other or they should be equal. Okay. So this is an important property of a matroid. Okay, so this is what actually leads us to greedy algorithms or problems which have matroid structure admit greedy algorithms. So yeah, so I'll just get back to this picture once again. So this is going to be the most intuitive part here. I mean, this is something we should all keep in mind. So it's easy to imagine this Hasse diagram for the Boolean lattice, what we call as Boolean lattice. Okay, I hope everybody is familiar with the term Hasse diagram. Okay, so we draw the sets. So at the top is a full set, that is 1 to n, we call as the universe. At the bottom, empty set. So we write sets of cardinality 1 here, so which are say 1, 2, etc., up to n, and sets of cardinality 2 above it, say 1, 2, 1, 3, etc., n minus 1, n. Okay, and so on. So now we draw edges from lower layer to the upper layer based on inclusion. Okay, so this edge is drawn if the sets are contained. We say set is contained in the set above. That is, 1 is contained in 1, 2, 1 is contained in 1, 3. We'll use a different arrow. 2 is contained in 1, 2, and so on. Okay. So this is something you're familiar, I believe. The Hasse diagram of the subset lattice or Boolean lattice, it's called. So it is the corresponding partial order is a subset relation. So here now, if you take any two elements, if there is a path from one element to the other, then you know that this element is less than or equal to that element. So that is, let's say, if there is a path from, let's say, set B to set C, then you know that B is a subset of C. That is, with respect to the partial order, B is less than or equal to C. Okay, so that is, though the partial order is not important to us, I mean, it's just intuitively it helps us to understand the structure of matroid or the structure of a matroid. Okay, so yeah. So now let's consider any matroid. So M be any matroid, E to E and I. Okay, so let's say E is 1 to N. Then I is a subset of the power set of 1 to N. That is set of all subsets of 1 to N. Okay, so let's color. So with green, the green colored dots are exactly elements of I. So these are elements of I. The set of all independent sets. Okay. Now this property that we saw now, that is all maximal independent sets are of the same cardinality. That basically says, so let's say size of a maximal independent set is K. Okay. So in this Hasse diagram, so we'll have green dots only up to layer K or K plus 1 if you call this as layer 1. Only up to layer K plus 1, that is size of set being K. And so all bases appear here. Okay. So if you look at, that is all maximal elements. That is, if you look at any green element here at the layer K, the outgoing edges will all be to non-green vertices, okay, or non-green points in the lattice. Okay. So that means all maximal element lie at the same level, what we call as. Okay. So now, how does it help? So what will be a greedy algorithm here, a natural greedy algorithm here? So a greedy algorithm, I mean, so then what is the problem here, right? Okay, I have a matroid, then when I keep on saying greedy algorithm. So let's consider the greedy algorithm as the following. Okay, you are given a matroid, probably in an implicit form, maybe as a graph or whatever. Okay, your objective is to compute a maximal independent set out of nothing. You just know the matroid, that is, given a set, you know how to check if it is independent or not, nothing more. Okay, then a natural way is you start from empty set, keep on adding element so that you have the independence property. Okay, so now there is at least one, so because a matroid is non-empty, there is at least one set of cardinality 1, right? So you just greedily search for which one fits, whatever. So you start with 1, 2 and so on. If 1 is independent, you just include it. Okay, so if 1 is independent, you just take that set. Let's say some I is independent, so this is the first step I take. Okay, then I keep on looking for adding ability to add elements so that I'll grow. Okay, so keep on doing it. So the claim is you'll always end up here, in the sense that at the kth layer or K plus 1th layer. Why is that?
Maximality property of elements at level K.
But why is that you'll always end up in layer K? You won't stop before. So when will you stop? You reach a point, a green point, where all its outgoing neighbors are non-green. Let's call it as blue. So why is it that you won't stuck at a point where everybody is blue?
Because of the independence, we will.
Okay, so what property of independence? What specific property of independence?
We no more longer remain independent if we include more elements, go higher in the.
That is true, but why is it that we will never get stuck? We'll always have a choice to go up. So when will we stuck? We'll stuck at a point where all neighbors are blue, right? All upward neighbors are blue. So why can't we get stuck at layer say k by 2 or some other layer?
If we get stuck at k by 2, then that means that the element at k by 2 has no neighbor in the upper level with green color.
Yes.
That means that
Yes.
is the maximal element.
Yes.
That is
Exactly.
the counter example, right? That
Yeah.
contradiction.
So yeah. So we cannot get stuck because of the exchange property or the property that maximal independent sets have same cardinality. So wherever we are getting stuck, that has to be a maximal element, right? Is everybody with me? See, the moment
Yes,
you
sir.
are getting, yeah, the moment you are getting stuck, that means we have hit the maximality. But the property that we have just proven now, I mean, which is essentially an outcome of exchange property of matroids, that is I3, says that any maximal independent set has the same cardinality. I mean, any two maximal independent sets have the same cardinality. That means I cannot get stuck anywhere. So I'll be just going ahead and ending up here. Okay. So this is kind of essential structure of greedy algorithms. Okay. So this exchange property of matroid essentially captures the greedy choice. Okay. The optimal substructure property is basically the subset closure of independent sets. That is, subset of an independent set is also an independent set. So all, I mean, with this matroid view, all we have to do is we have to define suitable independent sets so that independent sets form our solution space. So, and maximal independent sets will be our maximum sets or our optimal outputs. Okay. Yeah. So in the next picture, we'll just see if something is not a matroid. This exactly would happen.
Hello.
Okay. Yes. Yeah.
Sir, can you explain how are you relating this diagram to greedy algorithm? I did not understand that.
See, you can just see this process of taking a walk, right? Constructing independent set as a greedy algorithm. Okay. So the greedy choice, right, is guaranteed by the exchange property that you can always grow. So no matter what choice you made previously, you can always grow until you hit the maximum. Right? So that is a greedy choice property, right? Intuitively. So what is a greedy choice property? At every iteration, until you reach the solution, you are going to have a choice so that you can grow the solution. It's basically growing the subset, right? So
Is it like
the
growing the
property of
independent
matroid,
set?
it always allows you.
Hello?
Sorry.
Is it like growing the independent set of the matroid?
Exactly. So, I mean, basically, you're building an independent set. So, the greedy algorithm here would be to build a maximal independent set. That is the viewpoint. Your solutions set, right? Set of all solutions should be forming independent sets of the matroid. I mean, I'll make it more precise very soon. But yeah, the intuitive picture is what is important now.
Is the independent set of all solutions or solution?
No, set of all independent sets should be the solution space. So maximal independent sets should be the solution, optimal solutions. Others should be the partial solutions or whatever we call it as.
Sure, sir. Thanks.
Yeah. So yeah, we'll be demonstrating it. So yeah. So just for concreteness, let's just visualize when something is not a matroid. Okay. So the green dots here don't represent a matroid because you can see there are maximal elements at layer k plus 1 as well as layer k. Okay. So this is a maximal element at layer k. This is a maximal element at layer k plus 1. Hence, it's not a matroid because we know that maximal elements should be at the same layer for a matroid. Now, what will go wrong if you do a greedy algorithm or if you try to construct a maximal independent set? So this is one good path where we stopped at layer k plus 1 because k plus 1 is the maximum cardinality independent set, let's suppose. Okay. Now, if you take this blue line or light blue line, okay, See, because it's greedy choice, right? We don't really know what are the choices we are making and so on. There might be in some cases some intelligent choices, something minimum weight or minimum label, which might work. It depends on the situation. We are looking at a more general viewpoint. So in that case, such an algorithm, any such algorithm is going to fail. Okay. So you go on and stop at this, say, layer K, where all neighbors are blue, non-green. That means this happens to be maximal independent set. Okay, but this is not maximum because there is an independent set of cardinality k plus 1. And of course, it's not independent set because it's not a matroid, but I'll use the term. Okay, so this is what happens when, particularly for problems which do not admit greedy algorithms. Okay, so where you can trace a path, you'll end up with something maximal, but it's not maximum. So some people call it as local maximum or whatever. Okay, or some people also call it as Pareto optimal because you cannot improve it further. Okay, so yeah, so this is essentially non-matroid situation. Okay, so non-matroid. So whenever you are asked to design a greedy algorithm or talk about greedy algorithm for a specific problem, all you have to do is you come up with sets which represent the solution space or partial solutions as well. Okay, and see that all maximal solutions have the same cardinality, but there should also be this matroid structure because it should be closed under subsets and should satisfy the exchange property. Then you are ensured that there is always a greedy algorithm. Okay, which is basically tracing a path from empty set. You just keep on adding growing sets greedily, in greedy fashion. Greedy means whichever fits the best. You are guaranteed that you will not stop until you obtain optimal solution. In the cases when there is no matroid structure, there is always a possibility of a path. It again depends on the problem. I mean, it might be you might be able to make a clever guess into this path always, which was the case in scheduling algorithm. We'll discuss it shortly. Whereas in general, it may not be possible. So in the case of matching example, I didn't really discuss it completely. Yeah, I'll formulate it as an exercise for you. There are maximal matchings which are not maximum, which are not the maximum possible. So hence, if you devise any greedy algorithm, you can always construct an example graph where you can fool the algorithm to take this kind of path, where you will end up with a maximal matching which is not maximum. Okay. Yeah.
Sir, I have a question.
Yes.
Can you go to the last slide?
Yeah. Previous slide, right?
Yes. Here we are saying that all the solutions or all the sets that we reach at kth level are solutions, and anything below that is a partial solution.
Yeah. So
right?
yeah. So I'm just saying, let's call it as partial solution. I mean,
okay,
the problem.
But,
yeah.
All the solutions at kth level are optimal, or only one of them would be optimal?
No. So for in this case, it's all are optimal. So our job is to construct a maximum subset, maximum cardinality subset. So in this case, all will be optimal. If you have some weight constraints, then may not be all. Only some will be optimal.
Okay, sir. And which property are we calling as optimal substructure property?
So the optimal substructure property, so I'm just vaguely putting it as the subset property, right? Subset closure of independent sets. If A is independent, any subset of B is also independent.
Got it.
That's kind of formulating the optimal substructure property. Yeah, it's not precise. There is some catch to it. I mean, like I said, when you say optimal substructure, what do you really mean, and so on. So here we just say subset closure. So that is any subset of the independent set is also independent. It also means any subset of the solution is also solution. There is no optimality because so optimality is with respect to cardinality, right? So that way, yeah.
Hello.
Yeah.
Sir, can we go to the non-matroid example?
Yes.
Sir, you don't understand this part. Like, what was the question that we are dealing here? Question is that we're trying to find out the maximal subset in the cardinality in the set I starting from
maximum. Yeah, maximum cardinality subset.
in the set I,
Yes.
starting from 5 by drawing edges.
Yes.
And you're saying that we may end up in a green at level k, whereas there exists an element in level k plus 1,
Yes.
which is the maximum.
Yeah. Particularly when the structure does not satisfy Matroid properties.
So, like, it does not satisfy the third property.
Yes.
Because of that, you are saying that greedy algorithm may end up.
No, it's basically when the property that all maximal subsets have the same cardinality, that is not satisfied. So then this will fail. I mean, then this is just an intuitive. See, I mean, don't worry, don't break your head too much about it. Okay, so we're doing things formally now, but this is just an intuitive picture that I would like everyone to keep in mind. So when you grow, whenever you see a greedy algorithm which grows sets, this is how it looks like.
Okay.
So if the Matroid structure is not satisfied, so if the Matroid property is not satisfied, particularly I3 is not satisfied, this will be the situation. There will be independent sets at various layers. So it could be that a greedy algorithm is likely to be drawn into a fake or a bad path which gets stuck at a smaller layer or a lower layer than where the maximum cardinality set is sitting. So that is all. Yeah.
Okay.
Okay, so yeah, I'm just going to formulate what we call as maximum independent set problem for a Matroid. Okay, so here, say I'm not worried about complexity right now. Okay, so I'm only worried about having a meta structure for greedy algorithm. So I'll assume that a greedy okay. And that it's quite expensive, right? So even with the ground set being n element, I has the potential to be of size 2 to the n. Okay. So in that case, so for example, even for a graphic Matroid, right, number of spanning tree could be exponential. It can be really, really big. It can be roughly n to the n or n to the n by 2 or whatever. Okay. So where the number of edges is at most n square or n choose 2. So typically Matroid will be implicit. Okay, so the problem, I mean, you are given a problem, you have to define the Matroid, but the only thing that we need is given a subset, it is independent or not. That's essentially like saying, okay, is this solution feasible or not, or is it a partial solution or not? So the output is a basis that is a maximal independent set. Okay, that is the requirement. So a generic algorithm, like I mentioned in described it pictorially, this is a precise description of the algorithm. Okay, so you start with the empty set as independent. So now you repeatedly, you just successively try to add element. So choose any x. So in this, we didn't say anything specific. There is no weight as such given to us. So it could be minimum index or whatever. But we'll just say choose an x, whichever fits the best. Okay. Such that if you add x to our independent set being built, if this remains independent, then you keep on adding it. If no such x exists, you halt and output I. Otherwise, you add x to I and proceed. So this is exactly the procedure that I had described through this diagram. Okay, so you start with the empty set, you keep on adding. So how do you add? We just say arbitrary choice right now. We're not, and maybe somebody comes with an educated guess depending on the problem and so on. But this is how it looks like.
Sir?
Yeah.
Should it be E or power set of E?
Which one?
Third step.
So we are adding an element, one element at a time. So it's E. We're not adding a subset.
Okay.
So you're growing one element by element, right? So
Sir?
it should be E. Yeah.
So in the non-matroid example, you went from like there were many paths, right? So that's why you could give an example where you said even if in K I find local maxima, there's a possibility in K plus 1 it will be the global maxima. Here if you choose any arbitrary E, like arbitrary edge, then how is it, like do we try for many repetitions or?
No, that's what I'm saying, right? I mean, this, so when you say choose this edge, okay, so when you say choose this edge, we didn't specify any criteria. So in your specific algorithm that you have designed, there might be some criteria, okay? But
Okay.
if so, in most of the cases, such a criteria usually does not lead to ensure that a path is like this one, okay? So most of the cases, you can always construct an example where you can force the algorithm to take this path, okay? So when you say arbitrary, certainly this could be a potential choice, this could be a potential choice, this could be a potential choice, and so on. So algorithm could be drawn into those choices so that it makes a mistake. Okay.
So
But
sir,
this is not a
when we are,
provable statement.
okay.
Yeah.
So in that way we might not get k plus 1.
Exactly. So that's what I'm saying. The greedy algorithm will fail. That's what we were saying. Yeah.
Okay.
Yeah. So this is the greedy algorithm that I had described pictorially. So let's just compare this with the generic greedy algorithm. Okay. So it's pretty much the same as generic greedy algorithm. Only thing is there is a matroid structure here we are assuming. So the generic greedy algorithm, if you remember that I had mentioned 2 lectures ago, it was basically you start with the initial solution and keep on building it. Okay. So only thing that I had changed here is S changed to E. That is it. Otherwise there is nothing. So only specific thing is there was an update S here, whereas we didn't have any update here. That's all. I mean, update this again, it's just to ensure that you don't have to choose. I mean, you reduce your search space. That's all. Okay. That's again could be specific to the problem. So here, since we are choosing an element from the ground set, we don't have to update. That's all. I mean, in the case of matching, right? I mean, we had a greedy algorithm for matching where updating helps because all edges which are incident on the already matched edges, they can be thrown out. Okay. Otherwise, if you look at these two procedures, they are essentially the same. Okay. Sorry. Yeah. So any question on this? I'll just go back to the greedy algorithm. So let's just prove the correctness of this here. Just one line proof, but it's no harm in doing it again. Okay. So what is it we want? So we want that the output has to be a basis. Okay. So suppose I is the output of the algorithm. So when is I going to be output of the algorithm? For any x in E, well, there is a small thing catch. So this should be E minus I. Okay. Thus you can always come up with elements so that, I mean, I need that I union x has larger cardinality. Otherwise you can go on infinite loop, right? So then for all x in E, but not in I union x is not independent. So therefore, I is a maximal independent set. Therefore, a basis. I mean, which is a basis, of course. There's nothing else to prove, right? If you look at the algorithm, so when will the algorithm output I? So it halts and outputs only when there's no possibility of adding another element. What does it mean? But what is a guarantee? So if you look at the algorithm, you start with the empty set. Empty set is in I, right? Empty set is in I. And at every iteration, it's ensured that the set I, the invariant that we have maintained is set I is independent. Okay. So the moment you output I, we know that for any X in E, but not in I, you cannot add it so that it still remains independent. So in other words, it's a maximal independent set. Okay, so that is it. So that's a simple correctness. Yeah. So if there is any question, I'll take. So what we are going to do next is we'll use this meta algorithm. First, we'll do one small thing. It could be you want a minimum weight or maximum weight. So we'll do it for minimum weight. So minimum weight independent set. We'll see that the same procedure can essentially be adopted to minimum independent set. And as a consequence, we'll derive Kruskal's algorithm, where you see M as a graphic matroid. I are basically spanning forests of the graph. Then this procedure essentially can be modified into Kruskal's algorithm. That's what we are going to see now. Okay, so I'll give 1 or 2 minutes for questions.
Sir, in the correctness proof, that
Yes.
I is the calligraphic I that represents the independent set, or
Oh,
just one
no,
element?
no, that's why I'm bad at writing calligraphic I. That's why I wrote independent here. Okay. So this I is this I. Yeah, I
Okay, sir.
avoid writing calligraphic I in handwriting. Okay, I cannot write it properly. Yeah.
Hello.
Yes.
So this capital I, E minus I is also that small I there.
Small I, of course. See,
Okay.
otherwise it does not make sense, right? Calligraphic I
Yes.
is a power set. So
Yeah,
E
yeah,
minus,
that's what.
yeah.
Hello, sir.
Yes. Yeah.
Can we just go over the similarity between Matriods greedy and generic greedy?
Yeah.
I have a question there.
Yes.
So here we are outputting I, and the choice space is S in the generic greedy. Generic greedy, the choice space is S.
Yeah, see that's something we put it very vaguely there, right? Yeah, choice space is S, but it's not a solution space.
Yes.
Yeah.
It's a bit confusing because S is containing all the possible solutions.
No. Okay, so that I don't know how did I present the generic greedy algorithm there. Did I say S as solution space or choice space?
Just a second.
So if it is solution space, then it is you are not picking an X from the solution space. It should be X from the choice space.
So S was the choice space, sir.
Choice space, right? Yeah, it has to be the choice space. Okay, that means set of elements to choose from.
Yeah, okay. Then it's clear. Sure.
Yeah, so I mean, it's just notational. I just put this as E. I mean, usually even for matroids, people use S for ground set. I just put it as E because we are using the edge set for graphic matroid. So that's why it came as E. Otherwise, I could have just replaced it with the S. There's no big deal with the notation here. Yeah, so only thing, mild thing is I put this update as sense1, which is not really necessary in the case of matroid view. Okay, so I mean, even in the case of matroid, probably you could update E. You can throw away things which you cannot, you know for sure you cannot add it to I, those things. Is it fine? Shall we go ahead? Okay. So let's give a generic problem description. So here again, we are given a matroid, which is in implicit form, and a weight function, okay, for each element in the ground set. So for now, I'll just assume that non-negative, okay, so even negative weights, it just works. Just for simplicity, let's assume it's non-negative weights. So what we want is a minimum weight, maximum independent set. Okay, so please watch out. So that is so if you take this as a graphic matroid, we are looking for a minimum weight spanning tree. Okay, so or I could just write this as minimum weight basis in it. Okay, that is a basis be such that the total weight of the elements in the basis is the minimum. Okay, there could be multiple elements, multiple bases with the same minimum weight. That is, say minimum weight is k. Then there will be many. In fact, it could also be that all of them have the same weight. Okay. Is the problem clear? We are just modified, so we just have an additional weight function for the ground set elements. What we want is to minimize the weight of our basis. Earlier it was just okay, output some basis, we are happy. Now it has to be minimum weight. Okay. So now the solution happens to be fairly simple. Okay, it's just a modification of our algorithm. All we do is we order the elements. Okay, so we sort the ground set elements according to their weights. Say E1 to En is a ground set where so weight of E1 is the smallest, weight of V2 and so on. It's in ascending order. Okay. So now the procedure is pretty much the same, but only thing is we are trying to add elements in this order. That's it. So start with empty set for I equal to 1 to n. If I union ei is an independent set, then update I to be this. And at the end of this iteration, you would have built an independent set which is possibly maximum or maximal. Okay, so that's output I. So see, this is essentially greedy algorithm, right? This is basically the same greedy algorithm, but only thing is there is a specific ordering in which you are adding element. That means if you look at this, here you're actually tracing a specific path, or could be multiple still, because minimum, I mean, this weights could be equal for two elements and so on. In that case, there will be choices. If the weights are all distinct, then you're tracing a unique path here. You're basically, so instead of choosing an element arbitrarily, you're choosing with respect to this sorted order. Okay. Yeah, is the modification clear to everyone? All you do is you sort the ground set elements. Now the greedy basically chooses in the sorted order. That's all. Okay, so I'll not be giving an example. So the example will be Kruskal's algorithm for us. Yeah, so for now, we'll just stick to this algorithm and prove the algorithm's correctness first, and then we'll see how to, I mean, we'll see that this immediately gives us Kruskal's algorithm. Okay, good. So let's argue the correctness. I hope there is no question on the algorithm. Algorithm is clear to everybody, right? So the problem was to output a minimum weight basis. So all we did is we just sorted the ground set elements in ascending order, and we picked. So the greedy choice was with respect to that. Okay. Okay. So to prove correctness, so let's assume that output of the greedy algorithm is, let's say, G1 to Gk, and we'll also assume that so the output I is G1 to Gk. So this is my I. Sorry. Okay, so their weights are in ascending order, let's suppose. Now take any optimal solution. So one quick thing, is it that the number of elements in my output, that greedy output, as well as optimal solution, will they be any different? So am I justified in
Yes.
taking this as both as k, or will they be different? Yeah, so can you repeat?
Yes, sir. They both should be K.
They both should be k. So is everybody with me on that? Why is that? See, we didn't change the greedy algorithm, right? It's essentially the same greedy algorithm. Only thing is, you can just imagine. So this greedy algorithm that I have stated there is essentially the same. Only thing is, all I did is choose an x of minimum weight. So all, if I had just written here of minimum weight or smallest weight among the ones which is possible, then it's it. Nothing else I did. I just sorted it so that the choosing process is easier. Otherwise, it's essentially the same. I'm choosing minimum weight. That is, among all possible choices, I'll choose the minimum weight one. So hence, I'll certainly by the greedy property, right, or by the matroid property, that is exchange property or maximality condition, I'll hit the maximal. So that means I'll be outputting k elements. Okay. So hence, I'm justified in taking this as k, both the solutions being k. Okay. So even for optimal solution, let's assume that the elements are ordered in sorted order. Okay. In the ascending order. Now what we are going to do is we are going to compare this. So now what can you say about weight of G1 and weight of A1? So remember, when there was nothing, we chose G1 as a minimum weight one in the greedy, right? That's how we got it, right? Such that G1 is an independent set. G1 as a set, singleton set, is independent set. Now A1 is also an independent set. What does it mean? If weight of A1 was smaller than G1, we'd have chosen G1 as A1, right? Yeah. So in other words, what we have is weight of G1 is smaller than or equal to weight of A1. Yeah. So by the choice that we have made, weight of G1 is always smaller than weight of A1. Do you all agree with that? Otherwise, I would have chosen A1 as my first greedy choice, right? In the sorted order. Or in other words, in the sorted order, A1 would have come before G1, so I would have chosen that as well, because A1 is independent, right? Because I know that A1 to AK is an optimal solution, hence this itself is an independent set. Any subset of it is an independent set, so A1 is an independent set, right? Yeah, so now what we do is we just apply, yeah.
Sir, I have a doubt here.
Yes, yeah, please, yeah.
Shouldn't that be both the weights be equal? Only
That we don't know. I mean, see, this optimal solution is given by an adversary, right? We don't really know. And in the end, what we are going, yeah.
if weight of G1 is less than weight of A1, then we should definitely choose the G1 only, sir, in the first choice.
No. See, this is our choice. This is our algorithm. This is given by the adversary. Okay, so there is someone throwing at us. Okay, look, this is my solution better than yours. So we want to argue that, okay, no, you are wrong. That's what we are doing now. Okay. So we don't know anything about this solution except that it is optimal. That means total weight should be smaller, or at least claimed to be smaller. Okay, so we have no control on this solution. This is given by the adversary. You can just imagine there is an adversary sitting in front of us. He's throwing. Okay, so look, this is the optimal solution. Now prove that yours is better than mine. That's what we are doing. Okay.
Okay.
Yeah.
Excuse me, sir.
Yes.
Sir, is it possible that G1 and A1 are different E's, but the weight will be the same?
Eventually, yes, it is going to happen. But like I said, this is all we care about. Our choice is better than the choice of the adversary. Okay.
Right, sir.
Yeah. So eventually, yeah, it has to be. It has to be that they are equal or whatever. Okay. So it cannot be smaller. So hence they have the best way is if the total weight has to match, they have to be equal. Or in other words, our greedy. I mean, an optimal solution will be in fact a greedy solution itself. That's all. Okay.
Okay,
But
thank you, sir.
yeah, that's what we are going to prove. But right now we are not assuming anything. Yeah. Okay. So now by induction, I mean, I just didn't write induction. So for sake of induction, suppose an index I such that so weight of Gj is less than or equal to weight of Aj for all j up to 1 to I minus 1. Okay. So now we want to prove that weight of Gi is less than or equal to weight of Ai. Okay. So for that, so what we know is G1 to Gi minus 1 is independent. And of course, A1 to AI is also independent, right? Because A1 to AK itself is independent. Now, by the exchange property, there must be an index. Well, I just chose J. Okay, I'm sorry. Okay, this J and this J. Hope there is no confusion. There must be J such a way that G1 to Gi minus 1 AJ is independent. Okay. Yeah. But by the property of greedy, weight of Gi minus 1 should be less than or equal to weight of Aj, right? See, there is something that I didn't write here. I hope it is clear. So this AJ is in A1 to AI set minus G1 to whatever, Gi minus 1. It's apart from G1 to Gi minus 1. Because this statement is not interesting. Okay. By the exchange property, there is an element Aj which is not among G1 to Gi minus 1, such that if you add it, it's going to be independent. But then, what was my choice for Gi? So I chose Gi. Okay. So Gi is smallest among all those elements that can be added to G1 to Gi minus 1, so that it still remains independent. What does it mean? Weight of Aj, if not larger, it is, so yeah, weight of Aj should be at least that of Gi. Now this is in, so we chose this in ascending order. So that means weight of Aj is smaller than or equal to weight of Ai. Did I make sense? See, by the exchange property, we have an element. It could be AI or some Aj. Okay, let's assume some J. Okay, so that if I add Aj to G1 to Gi minus 1, it's going to be independent. But the way we have chosen, how did we choose Gi? Gi is of smallest weight, which can be added to G1 to Gi minus 1, so that it's still independent. So hence, it must be that weight of Aj is at least as much as weight of Gi. Now we have chosen this in, I mean, we have arranged this in ascending order. So hence weight of Aj, right? So J could be as well I. So it's at most weight of Ai. So that means what we have is weight of Gi is at most weight of Ai. Sorry. Okay. So therefore, weight of Gi, weight of Ai. So by induction, for all I, weight of Gi is less than or equal to weight of Ai. Sorry. What does it mean? That is weight of G1 to Gk is smaller than or equal to weight of A1 to AK. That is greedy algorithm is better. Greedy is better. Okay, so that is all. There is nothing non-trivial. Yeah, yeah.
Is AJ here the any potential candidate for GI and AI is the one that is in the optimal solution?
No. So see, this independent axiom, right? It basically says there is some element which you can add, right? Because the cardinality of A1 to AI is one more than cardinality of G1 to Gi minus 1.
So that what I'm saying is that AJ is the any potential candidate that we can pick for GI.
Yes, AJ will be among the potential candidates. Yes.
AI is the one that belongs to I, optimal one that has been given by the adversary.
Yeah. So A1 to AI are the ones which belong to the optimal one. So G1 to Gi minus 1 is the partial solution that we have built using greedy. So we are just staring at that stage of greedy algorithm. So what we have is, since this is an independent set of larger cardinality, by exchange property, there has to be one element which can be added to this. Let's call it as J, AJ. Okay. So that means G1 to Gi minus 1 comma AJ will be independent. But how did we choose Gj? So Gj is chosen. So among all elements apart from G1 to Gi minus 1 of smallest weight. So like you said, yes, AJ is one of the candidates among them. Yeah. So,
Okay,
so weight of Gi has to be smaller than or equal to weight of AJ. But the way we have chosen, it should be smaller than or equal to weight of AI. It could be that I equal to J. Okay. We have no control on it. And it doesn't matter. Yeah. So now if we apply induction, so this is basically an inductive proof. So what we have proved is for all I, weight of Gi is dominated by weight of AI. Or in other words, the total weight, if at all, will be higher for that of A1 to AK. But that is supposed to be optimal solution. So there is no other possibility but them to be equal. In fact, they will be equal. Okay, I'll not write anything here.
So the greedy choice ensures the first part of the inequality in the last point. WGI less
Yes,
than or equal
you're
to
right.
WAJ.
You're right. Right. Yes, exactly.
Okay.
This is the greedy choice. Yeah. Right. Okay. So now those who have seen Kruskal's algorithm, this is nothing but Kruskal's algorithm, right? Only difference here is checking if something is independent. That is nothing but seeing if the resulting graph is acyclic or not. Okay. Yeah. So we'll see it in the next lecture. I mean, we'll just specifically we'll see Kruskal's algorithm. So the plan for the next lecture is we'll see Kruskal's algorithm. We'll just rewrite this as a Kruskal's algorithm. Then the only part that remains is in implementing this. So then we'll bother about complexity. Okay, so we'll give an optimal implementation of Kruskal's algorithm using what we call as union find data structure. Okay. Okay, I'll stop here. Raghav, can you stop the recording?
Sir, I have one doubt. Can you go back to the previous slides? The slide where proof is.
Yeah. So the last slide, right? This one?
Yes. Sir, here how can we say that weight of AJ is less than or equal to weight of AI? Sir? Could you explain?
Yeah, because these are arranged in ascending order, right? So in other words, weight of A1 is smaller than or equal to weight of A2, etc., smaller than or equal to weight of AI. So AI is of the largest weight among A1 to AI.
Okay, sir.
Correct, no? Yeah. Yeah. Okay, Raghav, can you please stop the recording?